for second order, but first of the project was discussed. I don't need to do that, so I already discussed it. Now, for second order project, I will be a little bit more detailed for second order project, even though it was discussed already. First of all, make the following. You have a second order ordinary differential equation. You calculate its symmetry. And you are sure after this classification that you will have no symmetries, one possibility, then Brucker answer will not have it. You have one symmetry, again you don't have to completely integrate it, but you can use that symmetry in order to reduce the order of the equation. Instead of first order, second order, you will come to first order ODE, ordinary differential equation. Then you can see, anyhow it's some kind of error. Or you can find a conservation law. I'm not discussing it here, but having symmetries, you can find a conservation law between symmetries. It is the result of which is was first shown theoretically by Ibragimov in it was in 1918, and after that it was not used for a long time, but nowadays it became very famous. Even though Dr. she was a great algebraist, and she did not even want the word high-level to mention about the results that was art and calculations. But anyhow, it is philosophically very interesting and important result that each symmetry, provided that it has certain properties, it gives you a conservation law. Conservation law is like you had at school in the course of mechanics. It's something, some quantity which is unchanged during the movement of the system, during the system. Now, if you have two symmetries, then you use this method. If you have three symmetries, you can either use the three symmetries or subtract the two-dimensional subalgebra, which is also, it was shown, and it's easy to show, that in the complex domain, any three-dimensional algebra has two-dimensional subalgebra in the complex domain. Meaning that you make linear combination with coefficients which are complex. But then you will come to complex equations, and it's not that good. That's why it's better to discuss that. Suppose we have exactly two symmetries. Then there are four possibilities. What kind of algebra? It can be commutative, meaning that the commutator of the, so then it has basis. x1, x2, they are, because algebra is a linear space. So its basis has two operators. So I wrote it by x1, x2. Then it can be commutative, which means that the commutator of basic operator equals to 0. Then any linear combination of these operators x1, x2 again is commutative. They are commuting to each other, two operators. So that it is commutative algebra. Then you have commutative, but if you calculate this expression, just for application, I use it x1, this multiplication x2. It's just from the operator, the coefficients are taken like that, and it is not 0. Again, it is 0. This is not. It is also 0. Then the commutators are not 0 for x1, x2. Then you can make a change of the basis in your two-dimensional algebra so that the commutator of x1, x2 equals to x1. And again, you have two other passes for each other. It is not 0, this is 0. No other possibility. So altogether there are only 4. So it means that the equation that making two-dimensional Lie algebras can be changed into this form, Lie algebra, and then for them you calculate and disoperate introducing so-called canonical variants. I will show later on how they are obtained. You can come to these operators. This operator x1 and x2 can be taken in that form. In the case of 2, type 2, in this form, in 3, that form, and 4, that form. And how to find those variables that are called canonical, t and u, so that the operators x1, x2 become by base of power. And the result is given here, next sheet. So if your algebra of type 1, it means they are commuting with each other, and then x1 times x2 is not 0. Then you solve these equations for t, 2 equations, and 2 equations for u. So overdetermined system of equations for t, 2 equations for one unknown function t of x and y. Even though it is overdetermined, 2 equations for one variable, it is solvable because of the algebraic commutator relation. This is for ensuring that the system is solvable. And in this case, we have this, for the same for u, type 2, you are solving this equation and so on. Of course, you don't need to remember them. Just you take the textbook and I will never remember those equations. Nonsense to remembering formulas. There are so many of them. It's not rubbish in your head, so it's that you don't remember what is not absolutely necessary. So, you transform your equation to that form, and then they take this form. Each form is integrable. Here you see that you can integrate it twice easily, and here everywhere. So you can analyze yourself. You don't again to remember those equations because the presentation will be on the internet. You can take it or you can create the textbooks. So each time we integrate it. So now some examples. This equation, I like this equation very much myself because it shows many interesting things. You calculate the symmetries using the determining equation which I wrote before, and obtain that these objects are unique. All they are linear combinations. Once I remember that one PhD student who told that he learned the group analysis and he was calculating a certain equation, and for example, this equation told Professor, I could not come to your operation because it was something like that. My operator was minus 2x partial and minus y dy. So it is not the same result, but it is the same because it can be any linear combination, not precisely that. So linear combination in the sense you have to multiply by minus 1 and that's it. So having these two operators, you calculate, you solve that equation. So what is the type? Type, you obtain it just calculating commutators, and that multiplication, let me go back. So, and it is, I said that is type 3, yes? Let me see what type 3. Oh, okay. Type 3 is here. Type 3 even earlier. Yeah. So it means that commutator is not 0, and this bracket is also not bracket, but product is not 0. Therefore, I want to transform to that form. The operator is x1, x2. In order to do that, I solve the equations given. Yeah, for type 3. G is from there, U is from here. Substituting the expression for x1, x2. This is x1 and x2. You solve those equations for t and u and obtain these variables. Okay? Now, you have to rewrite your equation in terms of this variable. You maybe change your variables. But since the new independent variable depends also on dependent variable y, is always dependent. It's not that simple. Sometimes in the course of calculus, the formula is given only when independent variable depends only on the independent, new independent. That's a simple case. But anyhow, you can find out. It might be given. The simple way how to solve it in this complicated case, but probably in your other books you have time, maybe also very good way. So anyhow, how to, it's some kind of calculation, you have to make some calculation. So you simplify the equation and change variables and rewrite. Then your equation becomes like that. But in making change of variables, you should be careful. Sometimes you divide by something, it should not be 0, and so on. And then therefore it becomes some kind of special solutions which are singular solutions. We require that this should not be zero, otherwise it is a singular equation. And making all this analysis, we come to the following. After that you solve the equation, that this equation that I showed, this equation for analyzing those particular cases when it is not possible, those changes, you solve this equation. Of course, you obtain a solution containing two arbitrary parameters. But those singular cases give you only one parameter. So altogether you have three types of solutions. This is the general solution, in a sense that every solution has either this form or this or that, with plus or minus. So altogether 4 with this minus here. And none of them can be obtained from each other. They are absolutely independent. Then a question comes. When I was studying differential equations, we had this equation where the solution is given by certain formula, one formula for the solution. But here we have three formulas. And then when I was giving a lecture about this example, I had a question, not from students, but from teachers. They asked, it is impossible, because it's contradicting unicity theory. How the solution can be not unique? Because it's theory that the solution of any initial value problem with two initial letters it is unique, only one solution, but you have three. Now my answer, it is not contradicting, because if you have a given initial condition, you give, suppose initial point is x equals to x0 and y equals y0, and then y prime at the same point x0 is y1, for example. You have y and y prime are given, two data are given. So you have an initial data. Then this initial data itself make a good choice. Choose from all these four solutions, you choose what is appropriate to the problem. So I don't need to make any effort. The initial condition, they know themselves which is correct. After that you have a solution. But these solutions are, this one with one parameter solution, they are very interesting. I call them internal singularities. Because that equation which we had, let me show it again. You see this equation? No. Here. Of course, you see that x equals to 0 is singularity, y equals 0 also singular, because it cannot be by pattern. So these are external singularities, which you see from the equation without solving. And those particular solutions, they are internal because you should know the solution, but they are very interesting physically. If I come here, okay. So these solutions, the first one and second one, they are, you see, the straight line, for example, and these are some kind of like parabola or ellipse. If you draw the plot of these equations, of the solutions, you come to the following situation. Like that, and these are solutions given implicitly, because this formula gives you implicit solution. You cannot solve with respect to y. You cannot write y equals to certain fraction of x. So these implicit solutions are somehow attracted to those singular solutions. Meaning that through each point you can draw for each solution you can draw the singular solution, and depending on the y prime, what is the initial condition of the first derivative, it attracts to certain of the solutions, the singular solution. They are attracted to those solutions, very interesting solutions. But this is not a particular property of that concrete example. I found in analyzing many second-order equations which are nonlinear. Each time I came to the same equation, they always have singular internal singularities. I don't have any theory about that. I don't know why, but it's just pure observation. And of course, probably it is the same as it was discovered. What I was reading one of Paul Newman's papers. he was considering the question about singular solutions for first on the question and showed that they are invariant solutions. And these solutions are also invariant solutions. So that okay. So that is very interesting.
Linear combination of two generators, in fact, invariant solutions, linear combination of two generators.
Of course, yes. They are, because they are invariant solutions, yes. Thank you, yeah, okay. So, I finished. Oh, thank you.